Muy buenos días, tengan todos ustedes. La Academia Mexicana de Ciencias y la Facultad de Química de la Universidad Nacional Autónoma de México les dan la más cordial bienvenida a la ceremonia de ingreso del doctor Pascal Georges Lacroix como miembro correspondiente de la Academia. Nos acompañan en el presidium el doctor José Luis Morán López, presidente de la Academia Mexicana de Ciencias. El doctor Carlos Amador Bedoya, director de la Facultad de Química de la UNAM. El doctor Pascal Georges Lacroix, miembro correspondiente de nuevo ingreso e investigador del Centro Nacional de Investigación Científica de Toulouse, Francia. Y la doctora Rosa Luisa Santillán Vaca, investigadora del Departamento de Química del CINVESTAB. Saludamos también a los doctores Norberto Farfán García, investigador de la Facultad de Química de la UNAM y anfitrión del doctor Lacroix en México, y al doctor Guillermo Negrón Silva, investigador de la UAM Azcapotzalco, ambos proponentes del ingreso del doctor Lacroix a la Academia. Escucharemos al doctor Carlos Amador Bedoya, quien nos dirigirá unas palabras de bienvenida.
Perfecto. Buenos días, estimados miembros del presidio. Querido amigo José Luis Morán López, bienvenido a la Facultad de Química, bienvenido a este evento importante. Doctor Pascal Lacroix, welcome to Mexico again, welcome to the Chemistry School again, and congratulations on this occasion. Welcome over here. Doctora Rosa Santillán, bienvenida a la Facultad de Química. Estimados colegas, doctor Norberto Farfán, doctor Guillermo Negrón, muchas gracias por esta iniciativa. Invitados especiales, bienvenidos, colegas, compañeros, alumnos, etcétera. Bienvenidos a la Facultad de Química. Nada más quiero decir dos cosas muy breves, rápidamente. Es sorprendente, lo voy a repetir, la cantidad de cosas que hacemos en la Facultad de Química y la cantidad de eventos auspiciosos que tenemos. Como ustedes saben, el día de hoy tenemos la coincidencia de este especialísimo evento junto con la visita de Ada Yonath, Premio Nobel de Química. Tenemos mucho trabajo, tenemos muchas oportunidades de hacer muchas cosas muy importantes. Esa es una. La segunda cosa es que precisamente por eso y porque somos la Facultad de Química y participamos en la universidad y todo, pertenecemos a una familia de científicos que tiene amplísimas, por así decirlo, tentáculos que se extienden y nos agrupan a todos. Dicho de otra manera, estamos bajo la sombrilla de distinguidos científicos. Yo me di cuenta leyendo datos acerca de nuestro homenajeado del día de hoy, el doctor Pascal Lacroix, que hizo su doctorado con el doctor Oliver Kahn, con el profesor Oliver Kahn, y entonces fui a mi biblioteca y me traje el libro que tengo del doctor Oliver Kahn, y con eso me siento asociado con todos ustedes, con todo este esfuerzo. Y en esa situación es un honor para mí dar inicio a esta ceremonia gozosa, de gran prestigio, y recibirlos a todos ustedes, los que viven aquí en su casa y los que nos visitan en su casa también. Muchas gracias.
A continuación, la doctora Rosa Luisa Santillán Vaca, del Departamento de Química del CINVESTAB, presentará la semblanza del doctor Lacroix.
Buenos días a todos. Haré una breve presentación del amplio currículum del doctor Pascal, y no solo de su trayectoria científica, sino pues como persona, yo creo, hablando un poco con sus propias palabras. Entonces, les doy la bienvenida a todos también. Y bueno, voy a iniciar y lo voy a hacer en inglés. El profesor Pascal, Professor Pascal was born in Dole, and he's very proud to remind all of us that Dole is the town where Louis Pasteur, very important and famous scientist in the history in France, was born. He was born in the same town. He's married to Isabelle Malfant, who is also a researcher at LCC in the same place where he works. He has two beautiful children, Tom and Camille. Camille, of course, is now in the second year of chemistry, and her father is very proud of that. I will talk a little bit about his scientific career and how it started. He is an engineer from the National School of Chemistry of Strasbourg. And let me quote Pascal, how his career started. This is Pascal saying, as a student at the School of Chemistry of Strasbourg, I found once a paper of Olivier Kahn, his first mentor. So it became clear to me. I simply took a train and traveled 500 kilometers to meet him, arrived in front of him and said, I want to work with you. And this is Pascal. I think this describes a lot of Pascal. He's determined, he's very perseverant, and he likes to work hard. In 1989, Pascal received the PhD from the University of Orsay for his work in molecular materials and conducting and magnetic properties under the guidance, of course, of Professor Olivier Kahn, a pioneer in molecular magnetism and standing scientist. As a postdoctoral fellow, Lacroix entered the field of nonlinear optics, working with Professor Tobin Marks at Northwestern University. He returned to Orsay for a couple of years, and in 1994, he moved to the CNRS Laboratory of Coordination Chemistry in Toulouse, the place where he is working now. And there he developed a research program devoted to multi-property materials with nonlinear, optical, magnetic, and conducting properties. He was promoted to CNRS Research Director in 2004. At present, he has about over 100 publications and around 4,000 citations. Professor Pascal Lacroix' field of expertise is molecular switches and multifunctional materials with nonlinear optical properties. He has made original contributions in the field of photorelease of nitric oxide, second and third order nonlinear optical properties in metal ship-based complexes, push-pull boronates and tin complexes, and many other areas. And again, I would like to quote Pascal when he was asked, why is he interested in this field? And Pascal said, what is fascinating in molecular materials is that you can bring two properties on the same molecule in such a proximity that they must interact in some way. It is a bit like inventing new properties, getting new physical possibilities which were never before obtained. So that's why Pascal is so interested. He's always looking for combining different properties. And now I will also like to talk about this collaboration with the Mexican scientist. Pascal Lacroix, as one of the I don't know if, I think it was Carmen that mentioned, yes, Carmen mentioned in his talk before that his first contact with researchers in Mexico was through Dr. Emeritus Jean-Claude Taran. And he introduced him to Norberto Farfán in 1999. Since then, Pascal has been engaged in a long-time collaboration and co-signed more than 30 publications with Mexican partners that include Víctor Barba from the Universidad Autónoma del Estado de Morelos, José Luis Maldonado and Gabriel Ramos from the Centro de Investigaciones Ópticas, la doctora Itzia Padilla de UPIBI en el Instituto Politécnico Nacional, Norberto Farfán en la Facultad de Química y yo en el CIMBESTAB. Since 2004, he has received more than 15 graduate students. This started even before the LIA, of course, from the UNAM and CIMBESTAB for academic stays that go from 3 months to 1 year. That tells a lot about this collaboration. As Jose Guadalupe mentioned, and Carmen also, this is a really accomplishment of this exchange, academic exchange, to have students working in Mexico and also in France. Pascal Lacroix is responsible for the creation of the French-Mexican International Laboratory in Molecular Chemistry with application in materials and catalysis. It's called LIA, and at the beginning by the people responsible, who are Norberto and more Pascal, it was more like LIO, Leo, because it was very, very complicated getting to this really achievement. Officially, the LIA or LIA was created in Mexico the 21st of August, 2013. As you have seen, the collaborations goes back beyond this date. Lacroix has been the French director of the LIA and Norberto Farfán, the Mexican director. As a result of the scientific research of the LIA members, in 2017, it was renewed for until 2021, 4 more years. And we are all looking forward to be promoted to a UMI, which is a mixed unit of research. And it's even a step farther in the LIA. An important achievement of the LIA is also the creation of a cooperative agreement between the UNAM, the National Autonomous University of Mexico, and the University Paul Sabatier, which was signed in 2017. This agreement opens now the possibility for students to enroll in a joint program that allows them to get the degree from both France, the University of Paul Sabatier, and the UNAM. And this is very important. So far, there are 5 students already enrolled in this program, and we hope that many more students will join this opportunity. The collaborative work has received important financial support from many places, mainly the CNRS, CONACYT, ECOS North, the UNAM, and many other, on all the universities of all participants. Pascal Lacroix current research interest, as you have seen from the topic of his talk, is ruthenium nitrosyl complexes. And again, let me finish quoting Pascal. This is a rather new topic, having almost nothing to do with what I was studying 20 years ago. This is the way that the life of a scientist should be. As Winston Churchill said, to improve is to change. To be perfect is to change often. We thank you very much, Pascal, for your friendship first, for all the help, generous academic support that you have given us and many others and many students. And we thank the representative of the embassy for joining us. They have been also present since the beginning of this LIA or Leo, and they have helped a lot in contacting many people that have been important for this creation of the LIA. So with this, I thank you very much for your attention, and let's enjoy Pascal's talk.
A continuación, el doctor José Luis Morán López, presidente de la Academia, dará la bienvenida al doctor Lacroix y hará entrega del diploma de ingreso a la Academia.
Muy buenos días a todos ustedes. En primer lugar, quiero agradecer la anfitrionía del doctor Amador, que me estoy refiriendo a él realmente muy respetuosa, aunque nos conocemos desde hace décadas. Y detrás de nuestra amistad hay también muchas anécdotas y vivencias que hemos tenido a lo largo de los años y coincidimos en algunos aspectos de ciencia que nos ha mantenido informados sobre lo que hace uno y el otro. Cuando él resultó electo como director de la Facultad de Química, realmente me dio muchísimo gusto. Felicidades de haber tenido oportunidad de compartir un presidium con él, pero en este momento lo hago. Carlos, te deseo lo mejor para tu gestión. Doctora Santillán, muchas gracias por sus palabras. Realmente eso demuestra la calidad humana y científica que tiene la persona que recibimos hoy como miembro correspondiente de la Academia. Muy amable por sus palabras y por la reseña. Dr. Lacroix, I will speak English now, but later if I can tell you what I said before. Well, I was just having a chat with Dr. Lacroix, and he mentioned that he doesn't speak too much Spanish, but that certainly he's very happy to be in Mexico, that he's already for 20 years. The first time that he came here is about in 99, and since then he has come very often to continue with the collaboration. The Mexican Academy of Sciences is a group of scientists. Total amounts is around 2,800, and corresponding members is 113. The corresponding members, as you know, in other academies, is an honor for the academy itself, but also for the scientists to be member and recognize the role that you have played in developing science in Mexico. From what I heard just a minute ago, it is clear that the interaction with Mexican scientists, including Dr. Farfan and other people here in the table, has been extensive, and that we keep getting more from your input in a particular field that is molecular solids or molecular systems. My field is solid state physics somehow, so I understand a little bit of what you do. And I think you do certainly complicated things trying to put periodic arrangements of molecules. So this is a hard task for a theorist to calculate and to solve the problem electronically, but the applications are really very fantastic. So I also appreciate very much this field and where you are working. The other point is that I also read that you got your degree, your bachelor's degree in Strasbourg as engineer. And I had the time to spend a sabbatical at the university, the Louis Pasteur, in the group of Gauthier, Professor François Gauthier, who is a leader in magnetism, and I had an excellent time. The city is excellent, but the university and the group in magnetism has a long history of contributions to understand the properties of matter. So I am very happy that to have you here. I am very happy that you are joining us in this group of scientists in Mexico. You will be always welcome, and I really look ahead to hearing your conference. So thank you very much, and enjoy your stay. That I am sure you have excellent people that will host your time here in Mexico. So thank you very much, and let me just do the protocolary act and to just give you the paper that's so this is now the corresponding members of our very honored.
Doctor José Luis Morán López, presidente de la Academia Mexicana de Ciencias, doctor Carlos Amador Bedoya, director de la Facultad de Química, estimados colegas y amigos, lamento no poder hablar en español. Sin embargo, antes de iniciar mi conferencia, me gustaría tratar de decir algunas palabras en su lengua. Es para mí un placer y un gran honor recibir el nombramiento como miembro correspondiente de la Academia Mexicana de Ciencias. Quiero agradecer a todos los miembros de la Academia, especialmente al doctor Cecilio Álvarez del Instituto de Química de la UNAM, al doctor Eusebio Juasti del CINVESTAV y al doctor Guillermo Negrón de la Universidad Autónoma Metropolitana por proponer mi nombramiento. Pero no estaría aquí hoy sin el doctor Norberto Farfán de la Facultad de Química de la UNAM y sin la doctora Rosa Santillán del CINVESTAV. Quiero agradecerles especialmente por una colaboración muy productiva. Queridos amigos, les agradezco por una prolongada colaboración y gran amistad. Finalmente, deseo expresar mi reconocimiento al excelente nivel de la ciencia mexicana y agradecer el apoyo del CONACYT y el CNRS, que ha permitido fortalecer la relación científica y finalmente la amistad entre México y Francia. Una vez más, gracias a todos.
Damos entonces inicio a la conferencia del doctor Lacroix y solicitamos a los miembros del presidium que tomen su lugar al frente para escuchar la plática. Muchas gracias.
I know, maybe I need help. I don't know how it works. these people are my family, actually. Yes. It is not connected. Thanks a lot. So sorry, now I have to switch to English. But so the title is you have seen. I put it in red because I want to make sure that. Let me see how it works. Okay, everything will be devoted to NO, which is called nitric oxide as a single molecule, but as a ligand is called ruthenium. It's called nitrosyl, but it's still the same NO unit. This is the outline. It will be, the presentation is divided in 4 parts. The first, it's nitric oxide in biology. And as it's the first time that I write nitric oxide, I point out here, always when I write NO, I put a dot to remind you that it's a radical with 14 electrons. Then we'll see the NO release from this compound that you can see here. That was our first molecular target. Then, sorry, I go too fast. Then we'll see ruthenium nitrosyl complexes efficient into photon absorption, that I call TPA. Then an example of application against bacteria. That will be the most important part of the talk in relation to the title here. So let's start by nitric oxide in biology. Until recently, let's say 1990, nitric oxide, NO, was just regarded as a very toxic molecule, mainly produced by the industry and the cars. To illustrate, you have here the pollution in this city. I have checked carefully with a Mexican friend that it's not Mexico City. I don't know where it is, but it's not Mexico. Normally, NO, nitric oxide, is oxidized very rapidly in NO2, which gives the very characteristic brown color that probably is present here. Here it's London. It's the pollution of the air is in London. You can see that it's mostly due, it is here orange here, it's mostly due to the cars. So this is to say that NO is an important agent in the pollution of the air. Speaking of the toxicity of NO, I can say roughly 10 times less toxic than cyanhydric acid, which is already extremely toxic. Actually, I say roughly 10 times because it depends on the time of exposition. For instance, over a short period, let's say 5 minutes, HCN is far more toxic than NO, the lethal concentration. But on period of a few hours, NO becomes gradually more toxic. And here you have the recommendation by the World Health Organization. They say that the concentration in NO2 should be less than 40 micrograms per cubic meter. The situation about NO changed radically in about 1990 by the discovery of the endothelium-derived relaxing factor. So to make things short, you have certain muscles in your body, when they are contracted, that was an issue to know what makes them relax. That was a question for chemists, for biologists, for physicians. It was actually supposed to be a big molecule, a protein, a molecule having more than 1,000 atoms. And finally, it turned out that it's due to a very simple molecule having only 2 atoms, which is nitric oxide. After this discovery, nitric oxide was promoted Molecule of the Year by the journal Science in 1992. 5 years later, you have the creation of a journal called Nitric Oxide, which has a very rather good impact factor. And the year after, the Nobel Prize in Medicine was given to these 3 people who discovered the role of NO. NO has a key role in many biological processes. I summarize a few of them here. We have blood pressure regulation, action against cells development, neurotransmission, even male erection. For instance, you have to know that the very famous Viagra, very famous drug, favors the action of NO in vasodilatation. For all these reasons, NO donors have been intensively investigated. And you have a lot of books where you can find the application of NO and what kind of molecule can deliver NO. Some of them are purely organic, some of them are inorganic complexes. I will not speak of that. I will just focus on one that I think was important in the history, and it's a well-known molecule. It's trinitroglycerin. This one, as probably all of you know, it's a very dangerous liquid. It's the main component of dynamite. And it was surprisingly already reported in the 19th century by Murrell that this molecule had an action to cure heart disease. The reason is that when it's in the body, it gradually decomposes and it releases NO. Of course, at that time, people didn't know the reason for what it was a favorable effect, but that's it. So something important to say about NO is that depending on its concentration, its action can change radically. For instance, at very low concentration, 10 to the minus mol per liter, NO favors cell proliferations with possible action in tissue healing or tissue building. At higher concentration, 10 to the minus 6, NO favors cells death by apoptosis with possible application against cancer and inhibition of metastasis. So it's the cell proliferation, cell apoptosis is strictly the opposite process. For all these reasons, and also taking into account the fact that NO itself is very toxic, the NO release must be perfectly controlled, spatially, temporally, and quantitatively. And it's usually not the case. This is why ruthenium nitrosyl complexes are promising. They have appeared are promising NO donors for the reason that first, they are usually stable. They have a low toxicity. They are generally well tolerated by the body. And they can release NO under light irradiation exclusively. Also taking into account the fact that usually the light is highly controllable and it's not very invasive. And that's true that the interest for ruthenium nitrosyl complexes is largely due to their capacity to release NO under irradiation. Here, from the Science Finder, if you enter ruthenium nitrosyl as a keyword, you can see this evolution. I started that for the last 20 years. I started in 1998. It's when the Nobel Prize was given. Roughly, we can see that the number of papers devoted to ruthenium nitrosyl every year is multiplied by 5. And 2/3 of them are on the additional keyword NO release. So the NO release is illustrated here. Note that in the starting compound, the ruthenium is a ruthenium 2. It means a D6 configuration, closed shell, diamagnetic. And the NO is actually a cation, also diamagnetic. That is always the case when it's linear, for instance, here, ruthenium NO. When it's linear, you have a ruthenium NO. If it was bent, it could be possible to have ruthenium 3 and NO radical, but it's not stable at room temperature. It can be obtained at very low temperature, so in none of our compounds is the case. Also, this reaction, where NO is released with an extra electron, seems to indicate that any charge transfer transition to the nitrosyl should encourage the NO release. And that was actually our starting point in this investigation. This is our first synthetic target. You have NO here, and here we put a donor. In any case, the ruthenium nitrosyl is always very strongly withdrawing. Here you have the donor, which is a fluorine. In that case, it's an electron-rich pi-conjugated system, planar and fully delocalized. It means that the pi occupied level are high, therefore it's a donor. The charge transfer takes place from the ruthenium to the NO. Note that the torsion angle here is only 5 degrees. Actually, this is a value in a crystal structure, but in solution, the computation indicates that this angle should be about 30 degrees. That means that the charge transfer is could be not so good. Anyway, we know that the charge transfer is due to the overlap between the pi electron of this system and the pi system here. And a good assumption is to consider that this overlap is due directly to the cosine of this angle. So even with the 30 degrees, the cosine of 30 degrees is equal to 0.87, which means that we can assume to a large extent that there is a good overlap. So let's speak now. Let's speak of the release. This is the UV visible spectrum of this species. If you irradiate at 405 nanometers, you stimulate this excitation from the HOMO level to the LUMO level, and you can see the charge transfer from this donor to this acceptor. So the charge transfer is in accordance with this equation, because, again, to remove NO, although it's a cation, NO will be removed as NO radical, or NO0. Note also that there is an anti-bonding character between the ruthenium and the nitrogen. That means that during the transition, you decrease the bond order, and it will favor the release of the NO. That is probably an oversimplified mechanism. I will not speak too much of mechanism because it's still controversial. Anyway, I can say that according to theoreticians, but it's not sure, it's just an assumption, maybe when you absorb one photon, so when you promote the excited state, it's not a dissociative state. According to some theoretician, maybe after the molecule in the excited state is bent, and then it needs a second photon to be released. But it's still controversial. And I will not develop that. What is sure is that we can release NO. It can be shown chemically and physically. Chemically, by the use of the grease test. The grease reagent, it's a mixture of these two chemicals. That plays no role, it's just for a solubility reason. In the grease condition, the NO is first oxidized to nitrite, then you make a disonium, and then you end up with this pink dye. So the appearance of a pink dye, having the lambda max about 520 nanometers, indicates that you produced NO. You can see here, before you have this yellow solution, and under irradiation, you have a growth of a new band that corresponds to the appearance of this dye, and you end up with something that is pink, with a quantum yield that is 4.5%, which seems to be weak, but actually it's good enough for us, because if the quantum yield was too high, it would be very difficult to work with the molecule. The production of NO can be seen more directly by EPR spectroscopy, which require the species to be paramagnetic, like NO. This is the EPR signal without irradiation, so nothing happens. And after irradiation, you have a triplet that is characteristic of the NO. I explained briefly. Normally, it's a radical. You should have a singlet signal that would correspond to the magnetism of the spin of the electron. But then you have a coupling with the nuclear spin of the nitrogen, and you end up with 3 possible transitions that are characteristic here. Note also that in this kind of experiment, we have to trap the NO with such iron complex. Is due to the fact that the lifetime of NO is not very large. For instance, you have to know that in the body, the lifetime of NO is roughly 10 to the minus 3 seconds. It reacts extremely rapidly. So it works. We can release NO. But anyway, we are not fully satisfied. And now I will switch to photon absorption. You will understand why. This system have a photochemical weakness, which is that they require to be irradiated in a range 300, 500 nanometer, which means that it falls out of the therapeutic window. The therapeutic window is here. It's where the human tissue are roughly transparent, not completely transparent, but a little transparent. At higher energy, you have the absorption by melanin and hemoglobin. Here, at a longer wavelength, you have the absorption by water. So you have to work between 600 and 1300 nanometer. That push us investigating an alternative strategy, which is to use the two-photon absorption, in which one photon at 405 nanometer can be replaced by two photon at 810 nanometers in order to fall in a therapeutic window where the human tissue are relatively transparent. So this is not the main part of the presentation. I have to introduce a little bit the two-photon absorption, and first I have to say what it is and what it is not. So that, of course, is one photon absorption. Everybody knows what it is. You have a ground state, an excited state, and if you have a photon that has an energy equal to the energy difference, you can have the absorption. So now it's what is called, that is not the two-photon absorption. You absorb one photon, and after, so you reach an excited state, and during the lifetime of the excited state, you absorb a second photon, and you reach a second excited state. That is not two-photon absorption. That is excited state absorption. Two-photon absorption means that you absorb a photon and immediately you absorb a second one. And so here is a virtual state. It means that it corresponds to nothing. It's not a solution of a Schrödinger equation, for instance. That the absorbing two photons has to be regarded as a single quantum act. It means that the lifetime here, it's nothing. Here you stay here during the duration of this virtual state is typically 1 femtosecond, 10 to the minus 15 seconds. You don't consider it. Something important to say anyway is that the TPA is a universal property. It means that if you have if a molecule can absorb a photon, it could absorb also two. But of course, it doesn't occur in the usual condition. For instance, this molecule is a rhodamine B. It's an extremely good fluorescent molecule. If you make a solution of this molecule, a diluted solution in this molecule, in Mexico City in June at noon, and you go outside when the sun is really very high, each of these molecules will absorb one photon every second and re-emit by fluorescence. You absorb, you emit, you absorb, you emit, you absorb, you emit. It can also absorb two photons, but it will happen once every 10 millions of years. Of course, it means that there is something. It's possible, but it's more difficult. So for what reason? There is an answer at the physical level, and there is an answer at the chemical level. At the physical level, everything is due to this good-looking young lady called Maria Göper-Mayer, and she discovered that in 1931. It's important to point out that because at that time you had very few women in science. The concept of women in science is very popular in France now. I'm sure that if I was a woman, I'm speaking now for the Mexican woman. If I was a woman, I'm sure I would have been very attracted by studying the two-photon absorption. But it's so I encourage you to learn a little bit about two-photon absorption. This woman finally, and she got the Nobel Prize for this discovery. What she found is to make things simple. What you need is a very high power of light. For practical reasons, it means that it was not observed before the first lasers became available. That means 30 years after she thought it was possible. Today, it's usually done using a titanium sapphire laser working in the sub-pico regime. Sub-pico regime, typically, it means the duration of the pulse is 10 to the minus 13 second. 10 to the minus 13. That means that although the pulse is extremely powerful, the energy of the pulse, which is the power multiplied by the time, is zero or almost zero. That means that no energy is delivered to the body. That means also that there is no collateral damage. For instance, you don't burn the tissue. You do nothing. You do nothing except what you want to do, the two-photon absorption. Another thing that derives from the first one is that it is restricted to the vicinity of the focal point, because the phenomenon is proportional to the square of the intensity. Here, when you absorb one photon, obviously the absorption is proportional to the intensity of the light. Here, because you need two photons, it's proportional to the square of the intensity. That means that it takes place only at the focal point. I have to develop a little bit what I call the focal point. Here, you focalize the laser, and the focal point is here. It means that as you get closer to the focal point, the intensity of the light increase, of course, and you would say you end up, it's equal to the infinite. No, actually, it doesn't work like that. It's true that it's more and more intense, but after, it cannot be more than a higher maximum limit that is the same everywhere in a small sphere. What is important is to know what the dimension of the sphere is. The dimension of the sphere, the diameter of the sphere, is directly related, proportional to the wavelength of the light, and it's proportional to the inverse of this angle. But for practical reason, we can assume that it's roughly 10 micron. 10 micron, it means that you are within a cell, and you can work cell per cell. Because immediately when you leave the cell, you lose everything. I illustrate here. You have this sphere. So the two-photon absorption is the same everywhere in this cell. But if you go at a distance that is equal to the diameter of the sphere, the TPA absorption here is only 1% of what it is inside. It means that you decrease the phenomenon immediately when you leave the sphere. And definitely you can work cell per cell. Now, at the chemical level, what do we need if we want to do the two-photon absorption? In other words, how to quantify the TPA property of a molecule. So when you have a one-photon absorption, when you write the absorption proportional to the intensity, and this parameter leads to the extinction coefficient. When you write the same here, but when you say that it's proportional to the square of the intensity, this parameter leads to the cross-section, which is more or less the same as this one. It plays roughly the same role. It is the cross-section is given in Göpper-Mayer in relation to the woman who discovered that. Something interesting is that the cross-section can be computed. The cross-section is related to this equation. This involves the laser. It doesn't involve the molecule. And I want to give you the chemical response. That involves the molecule. So let's focus on that. This is the imaginary part of gamma. Gamma comes from this equation that is well known for people interested in nonlinear optics. This is the polarization of a molecule induced by an electric field. This is a Taylor development. That is a polarization without field. That means the dipole moment of the molecule. This is the linear term. You have here the electric field. This is a polarizability. Here you have the quadratic hyperpolarizability. Here you have the cubic hyperpolarizability. This is this term. So beta, gamma, and so on are indeed NLO properties. They are at the origin of the molecular NLO properties. I point that out because in our collaboration with Norberto Farfan and Rosa Santillan, we always more or less worked on nonlinear optics. So that means that we should be familiar with that. So it can be computed. I give you now the equation. What happened? Sorry, I had a problem because the expression was so complicated that the computer turned crazy. But I don't want you to be afraid of this expression, because this expression is just to tell you how it works. And it's just to tell you that it can be computed, but it's extremely complicated, and finally we'll forget about this formula. In this formula, you have terms like that, which you have here a transition, a transition, a transition, a transition. I show you here. You have a transition from a ground state to a first excited state, and after to a second excited state, a third excited state, and then to the ground state. The summation is on all over the excited state of the molecule. Typically, our molecule have roughly, let's say, 50 atoms. If you consider 2 excited states per atom, it's finally not so much. So let's say we work with 100 excited states. It's not so much. This comes from the perturbation theory. With 100 excitation, you will have 1 million, 100 times 100 times 100 times of different terms like that. 100 times 100 times 100. After this one become fixed. So 1 million on different terms per gamma component. Because here I wrote like if they were scalar, but actually they are not scalar. They are tensors. This is a vector. Polarizability, it's a vector. The dipole moment is a vector. The electric field is a vector. That means that that is a matrix, which is a rank 2 tensor. That is a rank 3 tensor. That is a rank 4 tensor with 81 components. 3 times 3 times 3 times 3. So it's extremely sophisticated, extremely complicated. So if we want to have a clear picture, we need a drastic simplification. It's what we are going to do, a drastic simplification, but does it make sense? If you simplify so much, if you forget if you replace the million different terms by only one, probably it will be difficult to make the assumption that it's at the origin of the property. Anyway, it will show you how it works. And it's what I want to point out now. If we consider something strictly dimensional, so instead of 81 components, we have only 1 component. And if we consider that there is only 1 dominant transition to explain, you end up with this figure where the cross-section is due to only 3 different parameters. It's probably oversimplified. Sure, it's oversimplified, but at least it tells you how it works. It means that is the intensity of the 2 photon absorption. So the intensity of the 2 photon absorption is related to the intensity of the 1 photon absorption from here to here, the energy of the 1 photon absorption from here to here, and to that, which is the change in dipole moment occurring between the ground state and the excited state. That means the quantification of the charge transfer. It's a very important parameter, the charge transfer, here and in any NLO system, NLO properties. And actually it's interesting because it's exactly what we have here. We have an important charge transfer between the donor and the acceptor, illustrated here by the HOMO and the LUMO orbital. So if we measure the 2 photon absorption on our system, it is achieved here. You can see in the presence of the Grease test, you can see the appearance of a pink cloud. Why here and not everywhere? Because the phenomenon takes place only at the focal point. But that was observed. What we need now is to quantify this property. And that was done by a fruitful collaboration with the CIO, by a technique that is called Z-scan technique. We call it Z-scan because the cell has to be moved along the Z axis of the propagation of the laser. So remember, the effect is important only at the focal point. Otherwise, when you get farther, the transmittance of the signal is 1. And only when you are close to the focal point, it's different. You can have an absorption. To be really relevant, the cell has to be as thin as possible. So typically 1 millimeter. That means that you need almost no compound. 1 or 2 drops, it's enough. But on the other hand, the solubility must be good because you need molecules, of course. So the solubility has to be reasonably good, typically 10 to the minus 2 mol per liter, which is already significant in most cases. So that's why we incorporate this chain in our system. In any case, we measure the properties. Note also that the two chlorido atoms, ions, or ligands, sorry, the two chlorido ligands are here replaced by a bipyridine for the reason that when you have two chlorido, the NO can be here, but it can be also here. So you have always a mixture of two isomers that you have to separate. And it's usually difficult, and more than difficult, usually it's impossible. So in the case of bipyridine, the NO is always here, so you have always a single isomer. And that is the starting property, 108 G per Meyer for this system. Now let's try to get something more efficient. First, the push-pull approach. The push-pull approach means that we'll keep one charge transfer from a donor to an acceptor. The relevant concept is that of charge transfer, that is due to that. How to increase the charge transfer? We can increase the distance between the donor and the acceptor, for instance, by introducing here a triple bond, and we increase a little bit the efficiency. Or we can increase the strength of the donor by the addition of an extra donor, for instance, a dimethylamine. Roughly, following this approach, we double the cross-section, which is still not very important. It's a lot of work synthetically, but we gain almost nothing. Another possibility is to increase the dimensionality of the system. Having a system, we start from one charge transfer here. We can go to 2 charge transfer or 3 charge transfer. That was achieved here. And we have, thanks to our excellent collaboration with a group of Norberto, you go from 100 to 900, so roughly, it's definitely a great improvement. That is a good strategy. This molecule is due to Mago, who is present in the room. It's my pleasure to say it. How to explain this enhancement, and what does it really mean? When you go from that to that, you multiply by so much. We have to find an explanation, because in other words, it's why the cross-section is multiplied by more than 3. As a starting point, we could consider that this molecule is equal to 3 of such molecule, roughly. So we could say maybe we will find something that is 300 and 400. So why is it so improved? Let's start by the monomer. The monomer, we have seen that what is dominant is the charge transfer from the fluorine. It is the occupied level here. Then you go to the ruthenium nitrogen. Okay. What happened when you transpose to the trinuclear? Here, it's obvious that the mixing will have no effect. Why? Because if you mix this orbital with this one, they are so far from each other that they don't see each other. They will stay constant. You will end up with 3 levels, but having strictly the same energy. The situation is very different here. When these 3 levels are mixed here, we will see that it's very affected. So if I call pi, that is the orbital here, this orbital transpose here, it's A, this on B, this on C, so A, B, C. Actually, they have to be mixed and lead to 3 new occupied levels. I call them occupied level because this one is completely occupied. So these 3 levels are the new orbital, molecular orbital. It may be a little, if you think it's difficult, it's a result of the quantum mechanics. I don't know if it's obvious it's probably not obvious. For instance, to make things simple, when you make the dihydrogen, you have SA, SB, and you end up with 2 levels, SA plus SB, SA minus SB. Here it's the same, but as you have 3 center, it's a little more complicated, but it's the same approach. So here are the 3 orbitals. Let's look at them. Again, this one, A plus B plus C. This one, 2A minus B minus C. This one, B minus C. These are the 3 orbitals computed. Importantly, instead of being the 3 level here, now they are at different energy because they interact, because they are close to each other, which was not the case for the ruthenium nitrosyl. Importantly, the occupied level is higher in energy. The value is equal to J. That means that the donating capabilities are enhanced. It has to be clearly understood. If you increase the occupied level, you get something that is more donor. So if it's more donor, you will increase the charge transfer, and you will end up with an increased cross-section. That means that the property of the tris ruthenium nitrosyl is higher than the sum of that of its mononuclear component. In other ways, what we say frequently is that the property of the sum is higher than the sum of the property. And that's why sigma is multiplied by more than 3. We have to check if this prediction is real or not. We can do that by a UV visible spectroscopy. Starting from the monomer, we have this transition between the fluorine to the ruthenium nitrosyl. That can be measured by the UV spectroscopy. When we go to the trimeric species, we gain this energy, that is the computed value. So we can also measure that by spectroscopy. This is the measure in the molecular species, 451 nanometer, in the trinuclear, 503 nanometer. The energy difference is equal to 0.283, which is close to the computation. That means that this computed effect is real. And indeed, the cross-section is multiplied by much more than 3. What this value mean? I have to say that the first 2 years, we were always engaged in structure that had the cross-section around 100. And suddenly, when we go to 8 to 910 and 1,650, we can think, what does it mean versus the world record, for instance? Are we still, is it okay? Is it acceptable that, or do we have to expect much more? So it's what I'm going to address now. I will focus on that because the jump from 100 to 900 was very spectacular. So if we compare that, it's the best ruthenium complexes I have found so far for 2 photon absorption. But we are close to the world record here. The value is 17,000 G per Meyer. And we have 900 G per Meyer. So you can say their system is really poor. You should not even point that out. Anyway, there are things that have to be kept in mind. First, in nonlinear optics, increasing the size means always increasing the property. So even if I didn't know that, spontaneously, I would say this structure having 9 ruthenium, 1, 2, 3, 4, 5, 6, 7, 8, 9 ruthenium complexes is probably extremely efficient. So that is not surprising. The second point is that for practical reasons, there are many synthetic chemists here. Making that is probably much more difficult than making that. It's already difficult to make that. Making something like that, it's probably a big problem. So it's not necessarily a big deal to try to make the system the more sophisticated as possible. And also very important in material science, what is important is not really the property of the molecule. It's also how many molecules you can introduce in your device. That means that the parameter, the figure of merit, instead of the cross-section, should rather be the cross-section divided by the molecular weight. And if you do that, for this system, you have 0.66. That's true, it's less than that. In the trimeric molecule made by Mago, it's 0.85. We are still lower than that, but we get closer. We get closer, and also remember that what these people want to do, they want to absorb 2 photons. What we want to do, it's not that. What we want to do is to release NO. We want to use the property to release NO. It's like if I was telling you, with my computer, I need a cord for my computer, and the cord has to be a conductor. I don't necessarily need a superconductor. I need something that is conductor to bring some electricity to my computer. So it's the same. But anyway, what I'm saying here is that our system is efficient enough. I think we reach our goal. Some application, I hope I was not too long. It's the last application. It's an example of application against bacteria. So the bacteria is a Staphylococcus epidermidis. Staphylococcus epidermidis is not the most famous of Staphylococcus, which is Staphylococcus aureus. Anyway, it's the most common. You have it everywhere on your skin. This is a very common antibiotic called methicillin. The posology of methicillin is 3 grams per day for an adult. The minimum inhibition concentration, MIC, for the methicillin, it means the concentration that is required not to kill the bacteria, but to stop the growth of the bacteria. This is equal to 510 to the minus 6 grams per milliliter. It means for an adult, typically 35 to 40 grams. It means higher than the posology. In other words, Staphylococcus epidermidis has become resistant to methicillin. But what happened in our system? So here I will show you, we measure the turbidity in biological medium. It seems to be the absorbance, but actually the loss in the light is due to the scattering of the bacteria. So when they grow, you have more and more scattering. They grow, and after they reach a limit. What happened if you put 1/10 of the posology of methicillin? The posology, we have seen that it's not enough. So if you put 1/10 of the posology, you expect no effect, and there is no effect. We put also a little bit of this system, 70 microgram per liter. Really, it's almost nothing. It corresponds to roughly 5 milligrams for the entire volume of the body. It means not enough, and nothing happens. And then we irradiate. And this is the irradiation. That means that you inhibit completely the growth of the bacteria. I'm saying we inhibit the growth. I'm not saying that we kill the bacteria. It's something that is still under investigation. Do we kill the bacteria? Or the question is to know if it's an antibiotic effect or an antiseptic effect. If we kill the bacteria, it's an antiseptic effect. So far we don't know. So to conclude, basically, I will point out 3 things. First, with this system, we had the first observation that NO could be released under 2-photon irradiation on a ruthenium nitrosyl complex. We have seen that this system leads to enhancement of the efficiency of methicillin in bacteria inhibition by a factor of about 100 at very low concentration. And then we develop a strategy based on increasing the number of ruthenium nitrosyl units that leads to a cross-section value in the case of this molecule equal to 1,650 Gauss per Meyer. Now I have to acknowledge a lot of people. First, the French team and our laboratory. I have to point out especially Isabelle Malfont. Rosa spoke of Isabelle Malfont already. Isabelle Malfont actually is my wife. I'm a little... maybe she's watching us. So it's why I have to emphasize her name. But no, not only for this reason, because she was the first one in Toulouse working on ruthenium nitrosyl. So it was for another purpose. This was for the isomerization from ruthenium NO, ruthenium nitrosyl, to ruthenium ON, isonitrosyl. It's also a very interesting topic, but I don't speak of that today. So we have the different students. These people are involved at the step of the biological investigation. We have also here for the two-photon absorption. And the Mexican team, the two-photon absorption, Gabriel Ramos, and the collaboration, very fruitful here. Note that there are people that have their name either in Toulouse and in Mexico, because the work is done in collaboration that is engaged within the French-Mexican International Laboratory. And I will say very rapidly, this are started by a long collaboration initiated in 1999 with Norberto Farfan and Rosa Santillan. I don't know if you remember, Rosa and Norberto, my first visit, it was the end of October 1999, exactly 20 years ago. So it's a very good thing to remember. So I am the French coordinator, Norberto is the Mexican coordinator. All the people involved in this laboratory, we had 60 scientific publications, not only from our collaboration, everybody involved in the international laboratory, and 150 visits and a student exchange between France and Mexico. I wish also to acknowledge the continuous help of the Faculty of Chemistry. It started with Eduardo Barzana and Jorge Vasquez, and I'm sure it will continue. I acknowledge the CNRS and CONACYT and also the continuous help and support of the French embassy. Here I show you the name of only the Mexican people who were directly involved in this laboratory. So all of them they are the author of some of this scientific this publication. Most of them are from the UNAM. You have also other group in the Sinvestav, and you have 2 other centers in Cuernavaca first, and the CIO in León. A last slide to say that I come from Toulouse, which is here. Toulouse, I think, is the most Mexican of the French city. It's usually called the pink city because of the color of the bricks. It's very close to Spain, so we have also a relation with Spain. It's at 100 kilometers, but I have to say that I never went to Spain. Although I went several times in Mexico. This is the picture in Toulouse. We made airplane. We have also the rocket, Ariane rocket, that is maybe you know, it's important in Europe. And also the Toulouse Marathon, because those who know me know that when I was much younger and much thinner, I was a marathon runner. I run a lot of them. This is our laboratory in Toulouse. And I will finish by a last slide. So I said Toulouse is the most Mexican French city. It means that Mexico is present in Toulouse, definitely. But Mexico is also present in my family. I illustrate that by 2 pictures. One was taken at the beginning of the collaboration, and my daughter was wearing already a kind of Mexican jersey. And here, taken more recently, it's a Mexican dinner. We organize in my house, let's say once every 3 weeks, we organize Mexican dinner. It's always a great time. I have to say that on the table, except these 2 lights, everything is Mexican. Even the forks and the knives. Here are fajitas, here you have the tequila. I have to say that most things are gifts from Norberto and Rosa. So I thank you. I thank also all your group, because it's a great day for me, but I'd like that it's also a great day for all the group. I thank again the embassy, the academy, and the Faculty of Chemistry, and I thank all of you for your attention. Thank you. I gave our time to Itzia this morning, to itself. Sorry.
Okay.
And now
I want to give you hard time. No, not at all. It's very, very interesting. I think it's just for the curiosity of these effects, I mean, it's impressive the work that you are doing, and I congratulate you. But I was wondering, you have this compound with the nitrosyl and in ruthenium, no, and the chlorides. But then you changed to the bipyridine, and you said that was much more effective. But the bipyridine also has an effect in the ruthenium as photosensitizers and so on. Could this be an effect as well? Or?
Yes, there is. At first, we could think if you normally for those who don't examine precisely, it is observed that if you increase the number of pi electron, normally you increase the property.
Mm-hmm.
So going from the replacing the 2-chlorido by a bipyridine, normally you should increase the property. Anyway, when you compute the transition, all the transition are due to the charge transfer from the terpyridine part to the NO. So the bipyridine is not engaged that much. We have tried also to incorporate the fluorine, which is here present on the terpyridine. We have tried to incorporate the fluorine on the terpyridine, on the bipyridine. It helps. It's more difficult. Chemically, it's difficult, but there is a little effect, but not so much as it is on the terpyridine. And finally, to answer completely your question, introducing a bipyridine increase a little bit by about 20% the properties. When you switch from chlorine to bipyridine, at best you gain 20%, but you don't change dramatically, and quantitatively you don't change the TPA property.
Okay, thank you.
First of all, thank you for your talk. It's very, very interesting. And just a simple question about what is following or what's besides this work by, for example, had you performed any ensuring studies with this kind of complexes in order to go to the application, for example, to photon apply?
Sorry, you spoke of ensuring studies. I'm sorry, I don't understand this word. What do you mean precisely?
It's a kind of graphage of these molecules into a surface or into a patch or a polymer in order to try to prepare a first prototype of application, because I think one of these applications is as a gas transmitter that could be advantageous for its controlled release.
You have seen that on bacteria, it works like that. We don't have, we can just put a little bit, there is no other thing to do, I would say. If you want now to enter the cell, if you want to fight against cancer, to be honest, I'm not saying that we will use that to fight cancer. It's a possibility. I don't see myself as a physician. I am a material chemist. So I propose molecules that are able to release NO because I know that there is a need for that. So to answer more completely the question, if we want to enter the cells, we know that with this system, the ruthenium can hardly enter the cells. So we need something else. We have started a program which is to incorporate a tail, actually an estradiol, that is compatible with biology to help the molecule entering. We discussed that with Pablo yesterday. It was already reported, or I don't know if it was published, but at least it was. You said, you show me an example. When you put this kind of tail, you have the system that can enter more likely the cells. So this system cannot enter the cell. So one possibility is to switch it to something that is more compatible. Another possibility, and I think it's more important to my opinion, it's to incorporate that in, for instance, nanoparticles. We are going to do that. There is a new scientist that will enter our group next year working on nanoparticles. Another possibility is to use downstreamers. Actually, we discussed that few days ago in Norberto's group, because the molecule can enter, if they are at this step, one per one, they can enter by diffusion. It means that it's not very efficient. But if you go to something bigger, you have a pinocytosis, or there are phagocytosis. There are other options. That means that the membrane of the cell itself goes and eats the species, which is funny. It means that the larger the species, the better it will enter, which seems to be counterintuitive, but anyway, is that. So we are investigating also in this direction. But so far, it didn't. To be honest, we didn't start it really.
Hi, sir. Good morning. Actually, you, I think, so, talk on the ruthenium odd nitroxide is very interesting, and I think we have not seen this kind of concept in the before. I think I thank you and appreciate your interesting talk. I have one question. In that sense, the single electron transfer. It goes single electron transfer. Single electron mono electrons transfer. It goes with the interchange spin state, no? But in the case of double electron transfer, it may not have that kind of possibility. But they might have a rotational and vibrational transition in the excited state.
Oh, I'm sorry, I think I do not understand the question. You are speaking of a single electron transfer. You mean a one photon?
One electron go to excited state.
From the ground state?
To excited state.
The ground state is a singlet state. So you're speaking of singlet to excited state singlet.
Yeah.
Yes.
But it is sometimes to go for the interstate changes, multiplity change, you know. But yes, in case of the double electron excitation, it may not have this kind of possibilities.
Sorry, I have a hard time understanding. What I can say is that according to the theoretician, we observe one photon. So we go, or one or two photons, it doesn't matter, but we go to the first excited state. We have the singlet excited state. After we go to a triplet excited state. It's very common in ruthenium chemistry. We reach a triplet state. And after there, it's what the theoreticians say. Then from the triplet state, you have a possibility, you go more likely to, I said, not to the linear form, but to the bent form that we call the metastable state 2.
Yeah.
Which is a triplet metastable state, and after you go back to a singlet, singlet metastable state. And after you have again an excitation to the excited state of the metastable state 2, which is normally dissociative according to them. I don't know. I said I didn't want to speak too much of theory because it's not very clear.
Okay.
So at this moment, I cannot say. I think it's still controversial. We don't know exactly what the mechanism is. What is true, I think depending on the molecule, the mechanism may be different. Because if we assume that 2 photons are required, from the definition that we have of the quantum yield, normally if 2 electrons are required, the quantum yield should not be more than 50%. What we call the quantum yield frequently, it's not a very good definition, but normally we say number of NO that were produced divided by number of electrons that were absorbed, which is normally not a yield, because a yield should have no dimension. And if you compare a number of molecules by a number of photons, so if you take this, usually we work with that. If you need 2 photons, the quantum yield will never be higher than 50%. But we have, in some cases, not often, but in some cases, we have ruthenium nitrosyl species having quantum yield higher than 50%. So that means that either the theoreticians are wrong, and we need only 1 photon, or it depends on the molecules. And I think it depends on the molecule.
Okay. The excited state might have some kind of vibrational, rotational phenomenon, no? In compared to the ground state. More than ground state, excited state, they have vibrational and rotational phenomena more than ground state, no? Is that taken into account in the equations?
Oh, no, we don't take that into account. We made a simple, that was our initial picture, and to have our clear mind, which is that we absorb one photon. That means we send an electron to the NO, which goes from NO plus to NO zero radical. We decrease the bond order, and by the vibration of the system, the NO is released. We take this simple picture, I would say, until we have a clear answer from the real theoretician. When I speak of me, I do a lot of computation, but I'm a computational chemist. I'm not a theoretician chemist. I'm speaking of the theoretician, those who create theories. So those who create theory and who examine that, they are not very clear about they don't know exactly how it works. So I would say I prefer not to interfere with them, to let them think, and when they have the proper answer, after we can speak with them. But again, I think that depending on the molecule, the mechanism is probably different. It's my feeling.
Yeah. Thank you, sir. Thank you very much.
You're welcome.
Thank you for the nice talk. I have a question. You quantify the photodissociation of nitric oxide by the grease test, but
By the, sorry?
you quantified the photodissociation by the nitric oxide for the grease test. Grease test. Is there another way to quantify this photodissociation where the acid condition are absent in this?
Yes, actually, we don't use the grease test to quantify. But that's true that maybe it was ambiguous because I gave you the quantum yield just when I show the grease test. Actually, we work in collaboration with photochemists, and to make this quantification, what we need is the UV visible spectrum.
Okay.
With the knowledge of the epsilon for the starting compound, for the photo product, and after we have a model that reproduce the kinetics, and then we can reach. We have to quantify how many photons are sent to the solution.
You quantify the azo compound, no? That you.
No. Sorry. No, we don't. When we measure the quantum yield, we don't use the grease effect.
Okay.
The grease effect is something to show with your eyes to make sure that it works.
Okay. Thank you.
Any other questions? Okay. If not, let's thank again Professor Pascal for his talk. This is for you to acknowledge your conference from the Faculty of Chemistry.
Thank you, Rosa. Thank you, all of you. I'm very proud and kind and happy to be here.
Thank you very much to everyone.